Hi, my name is Do, and I am the Virtualization Committee member of ICFP 2020 and the General Chair of ICFP 2021. Hope to see you all in the next year as well. I'd like to welcome you to session 6 of ICFP. The first talk is entitled Compiling Effect Handlers in Capability Passing Style. This paper will be presented by Philipp Schuster, and he will tell us about a language for effect handlers in capability passing style and an implementation of the language as a translation to simply typed lambda calculus in iterated continuation passing style.
Hi, I'm Philipp, and I present our ICFP 20 paper, Compiling Effect Handlers in Capability Passing Style. This is joint work with Immanuel Brachthäuser and Klaus Ostermann. Effect handlers are great, and more languages are getting support for effect handlers, and more libraries with effect handlers emerge. Still, performance is lacking. So this is about the performance of effect handlers. Now, there are two separate aspects to the performance of effect handlers. One, enabling compile time optimizations, and two, having efficient runtime operations. This work is strictly about the former. Effect handlers allow you to abstract over complex patterns of control flow. Yet, this abstraction comes at a cost. To this end, our first result is a theorem. I read it out for you. Full elimination. The translations of capability abstraction, capability application, do, handle, and so on do not introduce any residual lambda abstractions or applications, except for those in the translation of their subterms. What this means, intuitively, is that we fully eliminate all handler abstraction. Of course, this is only possible under certain conditions, and in the paper we formally state those conditions. When those conditions are met, we guarantee full elimination as per this theorem. A theoretical result is great, but what about practice? Well, we've conducted some benchmarks, and they look generally good. And in one case, for example, versus Coca, we see a speed up of 409x. Whoa! So what do? We define a source language, lambda cap, in explicit capability passing style. And we will see what that is in a moment. We then translate this language to simply type lambda calculus in iterated continuation passing style. We will also see what that is in a moment. This translation specializes effectful functions to the number of handlers they are used under. We then go on to define a second language, lambda 2 cap. It has exactly the same syntax as lambda cap, but a different type system. We go on to define a second translation, this time to 2-level lambda calculus. This translation specializes effectful functions to concrete handler implementations. So the important keywords are explicit capability passing style and iterated continuation passing style. Let's look at an example. I'll show you a little magic trick. I'll make all handlers disappear. And this will go in 2 steps corresponding to the 2 translations. Now, this is an effectful function, choice, written in our source language, lambda cap. It chooses a number between its argument n and 1. It uses 2 effects, flip for non-deterministic choice and fail for aborting the current continuation. It is written in explicit capability passing style, which means it explicitly abstracts over capabilities flip and fail, in lowercase here. If the argument n is smaller than 1, we fail, or else we flip a coin, and if the result is true, we return n, or else we recurse and choose a smaller number. Let's look at the handling side. Here, we first install a handler for flip. The handler for flip uses its continuation k twice and appends the result. Then we install a handler for fail, which discards its continuation k and immediately answers with the empty list. Both handlers introduce capabilities, lowercase flip and fail. In the call to choice here, we explicitly pass those capabilities to the effectful function choice. Each handler expects a specific answer type. The handler for flip expects a list because it appends the results of the continuation calls. The handler for fail also happens to expect a list because it immediately answers with the empty list. This is also why we wrap the call to choice into a singleton list. We call the list of answer types from outermost handler to innermost handler the stack shape. Let me illustrate why with a picture. This is the call stack at the call to choice. At the bottom, we have the handler for flip, which expects an answer of type list of int. Above it, we have the handler for fail, which expects also an answer type list of int. And then we have a frame which wraps things into the singleton list. Now, to approximate the shape of this stack, we have the list of answer types. In this case, it's a two-element list. The two elements are list of int and list of int. Because we've created the capability flip at the outer handler in a context with a stack shape with a single element, but want to use it inside of the inner handler, we have to fix the mismatch on the type level here and explicitly lift the capability. Guided by the stack shape, we translate our program to iterated continuation parsing style. It is like ordinary continuation parsing style, but with a twist. So the translation looks like this. We have the effectful function choice, and it abstracts over capabilities flip and fail. This is ordinary lambda abstraction. We then define a recursive function loop in iterated continuation parsing style. This means that it gets one or more continuation arguments. The number of continuation arguments is determined by the number of elements in the stack shape. Because we've used choice here under two handlers, correspondingly, in a stack shape with two elements, it now gets two continuation arguments. Capabilities are ordinary functions also in iterated continuation parsing style. For example, fail here gets two continuation arguments. And also in the rest of the function, for example, in the recursive call to loop, we also supply two continuation arguments. If we look at the handling side, we define capabilities, flip and fail. Flip is an iterated CPS, but in a stack shape with a single element and consequently gets a single continuation. Fail is an iterated CPS, but in a stack shape with two elements, so it gets two continuations. Now, we also see that lifting has operational meaning. Because we want to use the flip capability in a context where we supply it with two continuation arguments, we somehow have to fix this mismatch. So we define a new capability, lifted flip, which abstracts over two continuations, composes them, and passes the composition to the capability flip. The call to choice now gets 5 arguments. 2 capabilities, the argument n, and 2 continuations. So far, we've seen our source language, lambda cap, and our translation to simply type lambda calculus in iterated continuation parsing style. We've specialized effectful functions to the number of handlers they are used under. We want to go further and specialize functions to concrete handler implementations. As it happens, this program is also typable under the rules of our second language, lambda 2cap, so we can use our second translation to 2-level lambda calculus. This will specialize effectful functions to concrete handler implementations. It is the same as our first translation, except that we mark some applications and abstractions as static and others as dynamic. Specifically, we mark as static capability abstraction, the use of capabilities, capability definitions, the lifting of capabilities, and passing of capabilities to functions. This program now reduces to this. All handlers are gone. We've specialized the effectful function choice to the concrete handler implementations of flip and fail. We call the result of this specialization choice flip fail. The handler implementations have been inlined into the body of choice, and the continuations have been inlined into the handler implementations. This enables optimizations across effect calls. We are not looking up dynamically any handler implementations, and we're not searching for prompts on the stack or something either. We directly invoke the correct continuation. At the handling side, we see that the result is still in iterated continuation parsing style. This is okay. Now, let's look at those benchmark results again. We've benchmarked against different languages and different systems. The COCA language with effect handlers, an implementation of multi-prompt delimited control in JScheme, and effects as implemented in multi-core OCaml. In all of these, we see significant speedups, sometimes very big. In this benchmark, we see a slight slowdown, but still competitive performance. Interestingly, in the case of JScheme, we don't see a difference between our first translation and our second translation. This is because JScheme does all these reductions for us. We didn't have to extend the JScheme compiler or teach it any new tricks. It's just lambdas, inlining, beta reduction. To wrap up, we presented a compilation technique for effect handlers. Important concepts are explicit capability passing style and iterated continuation passing style. We are translating to just simply type lambda calculus. We don't need any special runtime system, and we don't need any special optimizations either. We have a theorem that guarantees full elimination under certain conditions, which we formally state in the paper. We have benchmarks, which show good speedups. And right now, we're working on integrating this compilation technique in a new standalone language called Effect. You should go check it out.
If you're interested in effect handlers and the implementation technique of explicitly passing them, we invite you to read our paper. At the Hope workshop, we will present our new language Effect and discuss its design. In another ICFP talk, our collaborator Ning Ning presents the important missing link between traditional effect handlers and explicitly passing them. And finally, she also presents her Haskell implementation at the Haskell Symposium. See you there.
Thank you, Philip. If you are watching this talk live as an ICFP participant, please look to see if there is a Q&A session available in your time band so that you can discuss this work with the author of the paper. We will now pause here to sync up with the talk schedule. Our next talk addresses the challenge of extending the meta-theory of Scala's core type system. This talk will be presented by Paolo Giarrusso, and the paper is entitled Scala Step by Step, Soundness for Dot with Step-Indexed Logical Relations in IRIS.
Hi everybody, and thanks for tuning in. Today, I'll present joint work with Stefanesco, Amin, Timany, Lars, Birkedal, and Robbert Krebbers, a new approach to soundness proofs for the dot calculus, the core of the Scala programming language. Before we dive into this talk, you might ask, what's interesting about the Scala type system? One might answer that Scala unifies functional and object-oriented programming, or has a very expressive module system. But what does that mean? In other functional programming languages, software modules are expressed through special constructs such as type classes or ML modules, which are not first class and require a special abstraction mechanism. Instead, Scala extends regular objects with abstract type members, allowing objects to serve as first-class modules. Hence, you can instantiate modules at runtime and abstract code across modules using regular Scala abstraction mechanisms, such as plain functions or even mixing inheritance. While abstract types appear in other sound type systems, Scala abstract type members are a significant challenge to our type soundness proof, because they gain impredicate type members, which are relative of type, colon type, and are challenging to prove sound. In a few slides, we will see a very small example. Where Scala is interesting, its type soundness has been, in fact, an open question since Scala's introduction in 2003. Soundness proofs has been machine checked for significant Scala fragments, the dot calculus, an amazing success. However, we have no proofs that abstract types are indeed abstract. And dot calculi lag behind Scala even on core features and are not catching up. Dot is hard to extend, while Scala's evolution is not slowing down. To create a more extensible dot calculus, our approach is to avoid syntactic proofs that use preservation and progress. Instead, we build a logical relation models to prove type soundness and data abstraction. Then, we retrofitted a version of dot over this model, obtaining a more extensible dot variant called guarded dot or G dot. Unfortunately, guarded dot adds certain guardedness restrictions, but in our evaluation, it seems acceptable. In exchange, G dot is more extensible, as we show through some additional features that we'll mention later. To make things concrete, let's now look at an example of Scala code. In this example, we create validator components that validate inputs from users. They provide an abstract type valid of valid inputs and a corresponding smart constructor make that validates its input and returns either valid data or nothing. Up to this point, nothing too fancy. However, new validators can be created at runtime, each with a distinct abstract type valid. Simplify the code, we had code the input type to be int, and we say that an input n is valid if it is greater than some constant k. The solution is in the next slide. Our solution is an object that defines a type of validators. Inhabitants of type validator contain two members: the type of valid inputs, valid, and the smart constructors make. Valid is declared to be a subtype of int, the type of all inputs. That is, type valid as int as upper bound, and implicitly, the empty type nothing as lower bound. These bounds encode that valid is abstract. Hence, inhabitants of valid can only be constructed through make. Function make validator maps input k to a validator that accepts only integers greater than k. For instance, here by calling make validator 0, we create a validator called pos, which only accepts positive integers, as shown by fails and walks. The type system rejects no because pos.valid is abstract, even though it is implemented by int, preventing users from bypassing our smart constructors. Thanks to first-class modules, we can also choose k at runtime, as done when creating legal ages. As promised, type legalages.valid is a distinct abstract type because legal ages is a different object with different validation conditions. This small example already uses many Scala features. So we see that in Scala, first-class modules with abstract types are encoded as objects with bounded type members. we have used the typing rule for type member introduction. A type definition type A equal T inhabits a bounded type declaration type A between bounds L and U if type T is indeed between bounds L and U. We have even used imperative type members. Types like validator with nested type members like valid are still regular types, not large types in some sense, and are subject to regular abstractions. So for instance, validator can in turn be a type member. Next, we sketch how we prove type soundness. We'll oversimplify this talk and leave the rest to the paper. Our model uses a logical relation. That is, we map each type T to a set V of T of values that behave as required by type T. For instance, intersection types are interpreted using set intersection. The set V of S and T is the intersection of V of S and V of T. Then we map syntactic typing judgments to semantic typing judgments. For instance, S is a subtype of T if V of S is a subset of V of T. Crucially, an expression E, a semantic type T, if E runs safely and any result is in V of T. Hence, semantically typed expressions are type safe by definition. Then we map each typing rule to a type lemma about semantic typing judgments that we must prove. For instance, type S and T is a subtype of type S because V of S and T is a subset of V of S. We now have a type soundness proofs that is extensible. Proving new typing lemmas cannot invalidate all once because each lemma is proved independently. Next, we show a naive model of imperative type members. We say that an object V has a type member A between bounds L and U if V dot A contains some type phi, which is indeed between those bounds L and U. Here, meta variables P and V range over sets of semantic types and values defined as follows. Types, a set of values represented as membership predicates, and values can be, among other things, objects, that is, finite maps from field labels to values or types. However, this definition is illegal, and because inlining some type shows that we're defining semval by negative recursion, which is illegal. This problem is exclusive to a setting where we have to model impredicative type members. Thankfully, abstract step indexing allows us to construct semval with a small change to our recursive equation. We must guard the recursion. That is, storing types into values must truncate types using the IRIS later functor. I won't explain what exactly that means, but we can ignore details and reason about the solution to this equation using the IRIS logic. Most of the logical relation will be identical to the naive model, except for type members. Since values only contain truncated type members, assertions about type members must be weakened using the later modality, as shown in this example. Here, a value V has type member A between L and U, if V dot A contains type phi, but later phi is between later L and later U. At this point, we can retrofit dot over this model, obtaining G dot. So we turn rules from P dot and upsilon dot into typing lemmas appropriate to the model. Each proof is around 2 to 10 lines of code. We add a type later T reflecting the later modality and associated typing rules. In this process, we obtain some stronger or additional rules. In other cases, the restrictions become more principal. For instance, abstract types are supported also in nested objects, as we have used in our example. We obtain distributivity of and or and other connectives, and we also obtain some typing for recursive types even beyond the typing rules in the upsilon dot variable. Here we show a few selected typing rules. Rules subtype cell subtype show that selecting a type member A from path P, which is a certain type, which is a type member between L and U, gives us a type which is between later L and later U. This reflects guardedness restriction on type members. Next, T coerce shows how we can eliminate later in many cases by adding no coercion to terms. Next, T braces I allows introducing recursive objects. To prevent certain circular typing derivations, we avoid the log fixes of other dot calculi and guard against recursive self-references by adding later to the type of self-variable x. This rule says that to create an object with definition x and give it type mu_x dot object type mu_x dot t, we must check that the definitions may have type t in a context where the self-variable x has type later t. Finally, dval allows to nest objects inside other objects. Unlike in PDOT, nested objects support abstract type members, and this is possible because of the restriction we added to the rule for object introduction. In the paper, we give motivating examples for some of our novel features. We scale this model to G dot, explaining how to deal with mu types, singleton types, path-dependent functions, full paths, and so on. We demonstrate expressivity despite the restrictions to type members. We give proofs about data abstractions, and we mechanize everything in CalCUS in IRIS. And our Soundness proof is of around 9,000 lines, and our examples take around 5,000 lines. For future work, we're extending our model to deal with type projections and higher kinds, additional Scala features which have not been supported by past dot calculi. We would like to find a way to elaborate two dot from calculi closer to Scala and to infer occurrences of later which Scala users currently do not have to write. And we hope that these techniques can be extended to other object-oriented type systems which support impredicative type members of virtual classes. In conclusion, Scala's type system calls for extensible type soundness proofs. So we design our type system using a semantics first approach. The challenge, or one of the challenges, was that impredicative type members are crucial for Scala's expressivity, but are hard to support. But luckily, using IRIS enabled machine checking a solution in a convenient way in Calc. Thank you very much for your attention.
Thank you, Paolo. If you are watching this talk live as an ICFP participant, please look to see if there is a Q&A session available in your time band so that you can discuss this work with the author of the paper. Our next talk is entitled A Dependently Typed Calculus with Pattern Matching and Erasure Inference. This paper has been written by Matúš Tejiščák, and he will tell us that erasure in well-typed programs is sound in that it commutes with reduction.
Hello, thank you for coming to my talk. My name is Matúš Tejiščák and I would like to talk about erasure in dependently typed programming. Dependent types are great. They let us write specifications and formulate invariants and let the computer help us make sure that our programs conform to those specifications. For example, here's a program that reads a binary number from the input, adds 1 to it and prints the result out, where the type of binary numbers is indexed by its unary representation, which is easier to reason about, which allows us to give the function add1 a type that guarantees that add1 indeed computes the successor of the given binary number. Unfortunately, just by looking at the types, we can already tell that this program will run in exponential time and space with respect to the number of bits read from the input. Why is that? Well, if we look at the implicit arguments, which are usually hidden and filled in by the elaborator, we can see that each binary number also contains the unary representation of the binary numbers contained within, and the function add1 also takes a unary representation of the binary number it takes. And those unary representations are exponentially sized with respect to the number of bits, and therefore the representation of memory looks roughly like this. The useful bit on the left is dwarfed by the compile time only information on the right. So in this talk I would like to convince you that this is a real problem, that we should really address this, and that by specifying our programs more precisely we should not make them run slower, and we should not make a linear program run in exponential time or worse, just by saying about it that it calculates the right answer. I'll sketch that irrelevance, erased universes or laziness all solve a slightly different problem, so they are not always applicable or not always the best choice. I'll sketch the gist of how we can discover this compile time only information that might be too big, and automatically discover it and remove it from the program, thus recovering the intended runtime complexity. And I'll show this optimization makes other optimizations more powerful, and also makes the compiler run faster because there's less code to generate. In language like Coq, we might attempt to use the erased universe of prop. However, while this is great for erasing proofs, it's not so good at erasing indices, as illustrated by the function nat to bin. Because what should be the type of n? Should the type of n be erased or not erased? Since function nat to bin requires n to do its job, n must have a non-erased type. However, because the same n is used as an index of bin, it must have an erased type. So tying erasure to a type of a variable is not useful in this case. We might even try laziness, that works sometimes, but it's a dynamic fix for a static problem. We can already tell at compile time which bits can be erased and which bits we need for runtime. So we should not keep a runtime check to prevent evaluation of that information. We should just erase it altogether. Laziness is not an option in eagerly evaluated languages, and as illustrated by the function server loop, we have a choice here between accumulating thunks in the variable n if we do not evaluate it, and therefore leaking memory, or evaluating it and having n explode exponentially in size. Irrelevance can also be used to achieve erasure. However, irrelevance is too strong. By irrelevance, I mean the property of sub-expressions ignored in definitional equality. This is a very strong property, and it's not necessary for erasure at runtime. In AGDA, irrelevance does not help us with the binary number example, just because it's too powerful and causes problems. Also, inference of irrelevance is harder than just inference of erasure. So if we just need erasure, we do not need irrelevance with all the consequences it brings. So what do we do then? Well, here's a small example. Function vlen that takes a vector and calculates its length. We can ask the question, can we erase the second argument of vlen called n? Or does vlen need to look at this argument to do its job? Well, in the first clause, the second argument is forced to 0, indicated by square brackets, because the vector is empty. So, since the types tell us that the second argument is 0, we need not look at it, we do not have to inspect it. In the second clause, the types tell us that the second argument is a successor of a certain number called n. So the types tell us the tag of the constructor, but they do not tell us what n is. However, on the right-hand side, n is used in the recursive call as a second argument of vlen. So if the recursive call does not need the second argument, we do not need n, and since we know the tag and we do not need the n, we do not need the second argument altogether, and it's consistent then to say that the second argument of vlen can be erased. To make this a little bit more formal, we need to get a bit more explicit about the pattern variables, so we insert the two lines starting with where that bind the pattern variables explicitly and give them types. Next, we number all colons and all applications in the whole program. So all name bindings are numbered now. Each of these numbers will eventually be replaced by a definite annotation R or E, retained or erased, but we cannot just fill in any annotations we like, because they need to satisfy some consistency constraints. So then we traverse the whole program and gather consistency constraints. For example, in this program we can notice that the annotation number 19 has to be the same as the annotation number 30, because it's the same function. It's the first argument of function vlen, so it has to have the same annotation. This is expressible in the horn clause form. Then on the right hand side we can observe that if s uses its first argument and vector length uses its second argument, then the pattern variable n needs to be available. This is also expressible in the horn clause form, and we can see it in the second line of the table. Finally, on the left-hand side of this clause, we can observe that if n has to be available, then s needs to remember its argument, which means number 32 has to be retained, and vector length has to retain its second argument, which means number 31 has to be retained. This is also expressible as two horn clauses, and in this manner we go through the whole program, gather the constraints, and then find the solution with that erases as much as possible while being consistent with these constraints. This yields an annotated program where every variable and every application has been annotated with R or E, and the annotations are built into the type system. It's not something we keep on the side. It's really built into the type signatures. So then we can erase everything that's annotated with E, obtaining the program that we actually want to run, and that does not contain any traces of overhead caused by dependent typing and indices. This erasure system has some nice properties. For example, the function subst does not retain its proof argument, so the proof can be erased, despite being matched on. The types tell us what the constructor tag must be. We know it's because there's only one constructor in the type family, and the argument x is not used on the right hand side. Therefore the proof can be erased and subst becomes an identity function after erasure. Of course, this is doable only if the type system is sound and does not allow things like non-termination. Erasure also helps the new type optimization, makes it more broadly applicable, and in combination with it, it can collapse large, richly indexed structures into just the bare bones representation, the meat of the structure. Finally, the identity optimization gets more powerful with erasure because it's much easier to spot that something is an identity after it's been erased. So weaken E is more obviously an identity than weaken. Finally, here are some benchmarks of my prototype implementation. The times shown include the whole compiler pipeline from parsing up to and including native code generation. And we can see that with erasure enabled, the total compilation time is much shorter because there's less code to generate. Given that we've shown that we can distinguish between compile time only information and runtime information automatically, we have shown that the commonly claimed lack of phase distinction in dependently typed programs is a myth. And it's true that the phase distinction no longer lines up with the distinction between terms and types, between implicit and explicit, but it's there and we can make use of it. So the main direction of further research is unification with QTT, which is Bob Atkey's extension of Conor McBride's work, featuring linearity as an additional quantity to erased and not erased. It would be nice to have erasure polymorphism or quantity polymorphism so that functions like apply can take erased and not erased functions. Finally, erasure can be inferred from a completely unannotated program. However, this has the same drawbacks as Haskell or an ML program without type annotations. You make a mistake somewhere, the system infers the wrong type, and then something very far away breaks and it's hard to find the real cause. Moreover, explicit annotation would help with separate compilation, so it would be good to find a convenient rules for explicit annotation that would help with both. Thank you for your attention. Questions are very welcome.
Thank you, Matúš. If you are watching this talk live, please don't forget about a Q&A session that may be available in your time band. The fourth talk of this session is entitled Raising Expectations, Automating Expected Cost Analysis with Types. Dee Wang and David Kahn will present the talk together, and they will tell us about a type-based analysis of deriving upper bounds on the expected execution cost of probabilistic programs.
Hello, ICFP and future viewers of this video. My name is Dee, a PhD student at Carnegie Mellon University, and today my co-author David and I are going to be presenting our work on automatic probabilistic resource analyzing language from our paper, Raising Expectations, Automating Expected Cost Analysis with Types, which is accompanied by an implementation we call PRAML, standing for Probabilistic Resource Aware ML. Resource analysis of programs is something that is of renewed interest in the modern day. Not only does it fulfill the traditional role of identifying performance bottlenecks, but also the following. If you care about digital security, you will need timing analysis to mitigate side-channel timing attacks. If you want to take advantage of the latest tech trends in smart contracts, you will need to be able to measure your gas usage. And, of course, if you care about our real world, it will sure help the climate to be able to consider the carbon footprint of the code running in data centers. There are just so many different resources in so many different programs. So the problem is that nobody has the time to go through and formally analyze all of them. For this reason, our work builds upon an approach of language-based automatic resource analysis. In PRAML, a programmer may code as per usual and just via type inference receive verifiably sound resource analysis at their fingertips. Now, so far, all of this already exists in PRAML's predecessor, Resource-Aware ML or RAML. However, PRAML can model something that RAML cannot, probability. Probability is increasingly important in modern algorithm design. Randomized and statistical algorithms are employed on mass data constantly to squeeze out every bit of efficiency. So it is crucial that modern resource analysis systems can cope with expected costs rather than just worst case. This is where our work on PRAML comes in. PRAML extends the worst case resource analysis of RAML to measure the worst case expected value. It is worth noting that the resulting language is also suitable for probabilistic modeling, and we will discuss a couple of these applications later on. Now, I leave it to David to talk about more about the meat of our work.
Thank you, Dee. Let's start by quickly going over how type system-based resource analysis works in a non-probabilistic setting. We will be using RAML's Automatic Amortized Resource Analysis Type System, or AARA. The idea of AARA is based on the potential method of amortized analysis set out by Robbert. What we are going to do is imbue the types at each stage of the program environment with some notion of potential energy, and allow the energy to change over time. The changes in potential energy between each step then describes the energy discharged to pay for costs. The key takeaway is this: the total potential needed at the beginning is an upper bound on the total cost. So, by typing the program with this notion of potential energy, we've bounded the cost. And AARA does this while still maintaining the compositionality of a type system. This technique even works for higher order functions and polynomial or exponential cost bounds. However, let's start small and make an example of the mem function, like that from the OCaml standard library list module. We will use AARA to bound the number of recursive calls. So here is a version of the mem function. Now, the mem function takes the naive approach of checking whether the argument x is in the given list. It iterates over the list, checks each element for equality, and returns true if it ever finds one. At worst, we might need to check the whole list, which means we could expect n recursive calls in the worst case, where n is the length of the list. We can show this using the potential method as follows. First, we explicitly mark the costs where they occur using tick operations. That would occur right here at the recursive call. Then we can type the list argument with 1 unit of potential per element, written like so, with a superscript 1 representing the amount of potential per element. This aligns with what we've just guessed the worst case cost will be, the length of the list. Then we can write the type of the whole function with this, where these numbers here on either side of the arrow represent the resources present before and after the function call. In this case, we can just let them be 0. Now let's move on to the interesting parts in the function body and see how we use these types with potential and how we match up with the function signature just provided. We first deconstruct the list, gaining the 1 unit of potential that was previously stored at the head of the input list. Then, if the head is the element we're looking for, we can just return true and drop all the remaining potential. Otherwise, we use that 1 free unit of potential to pay for the tick expression, and then recurse on the tail of the input list. To perform this recursive call, we check the potential in the current environment against the function signature. Because the mem function requires 1 unit of potential per element in the list, and the tail of the input list still has 1 unit of potential per element, this line type checks. And that's it. The potential we guessed at the beginning, 1 per element in the list, is the worst case bound we guessed, the length of the list. As a final note about this example, although we did it by guess and check, these types actually can be inferred. This is because all the relevant arithmetic we did to calculate these constants can actually be given via linear constraints. If we collect the linear constraints and solve them, we get our desired resource bounding type. This continues to hold for Praml in general as well. Now, the language we just saw is a subset of OCaml and non-probabilistic. So to make expected values at all meaningful, we extend it with what is probably the most primitive probabilistic operation possible, the coin flip. Specifically, we flip a coin to decide which branch of code to run. We can slot this new behavior into the RAML type system with some pretty intuitive rules. The flip rule deals with coin flip expressions, where the coin bias is a constant. In this rule, gamma is a typing context, Q is the initial amount of resources, A is the resource annotated type of the expression, and of course, P is the coin flip bias. So what this bottom part says is just that the flip expression type checks as A under context gamma with Q extra resources. The key idea of the flip rule is that the expected cost between the two branches, E1 and E2, can be calculated as the weighted sum of their respective typing judgments. And you can see here and here that we perform some sort of weighting by the flip probability P. We also allow for a more complicated case, where the coin bias is parameterized, as if it were a program variable. It turns out, in our implementation, that these two rules can be treated as special cases of one more general rule. However, despite the intuition behind these rules, they posed a problem. While these type rules do indeed turn out to be sound, the probabilistic nature of the new flip operations are incompatible with the operational semantics used in RAML's AARA. However, we need an operational semantics in order to show that the resource analysis is sound. To overcome this, we created a whole new operational semantics for Praml based on Borgström et al. 2016's trace-based and step-indexed distribution-based semantics. You can find the details of this adaptation in the paper. With operational semantics in hand, we can state soundness as follows. If expression E types as A under context gamma with Q units of initial potential, then the expected cost of evaluating E is bounded by Q plus the potential in gamma. This soundness statement should seem familiar. It is exactly the key takeaway of the potential method mentioned earlier. The initial potential bounds the cost. This holds even for programs that may not terminate. We can also say that if the cost model counts evaluation steps, then the existence of any expected cost bound at all implies almost sure termination. Now let's look at this new type system in action on a simple example. Here is the program Bernoulli, which performs a sequence of Bernoulli trials. When run, it has a 50% chance of recursing and a 50% chance of terminating. As many might remember from their Intro to Probability course, this results in a geometric distribution with expected value 2. Thus, while it could go on forever, we can actually give it a finite notion of cost. Let's check it now using Praml. Now, the only initial potential that Bernoulli needs is 2 units. 1 unit of potential is spent immediately on the tick. After the coin flip, we assign 0 potential to the head case because it returns immediately, and 2 units of potential to the tails case. Then in the tails case, we reuse the guessed type of Bernoulli, and it all works out. Because the weighted sum of the potential assigned to these 2 branches is exactly 1, the flip rule justifies going into these branches with only 1 unit of potential, even though the tails branch by itself would require 2. In the paper, we use this same automated technique on a variety of more complicated functions with more interesting resource bounds. For instance, we show that Praml can analyze the gambler's ruin, wherein 2 players, Alice and Bob, continually bet $1 against each other on the results of a coin flip until one player runs out of money. In the program, we model the amount of money as the length of a list. If the coin is fair, Alice starts with A dollars and Bob starts with B dollars, then this series of bets is expected to take A times B rounds. Our implementation infers this bound exactly. Praml can also infer non-trivial bounds with parameterized probabilities. The von Neumann function implements a mechanism to make a fair coin from a biased one. With some scaling trick, Praml derives that the function is expected to take 1 over p times 1 minus p steps, where p is the probability for the biased coin to show heads. Both of these examples also show that Praml can be of use in probabilistic modeling, as these are both probabilistic models. Here are some tables of various other analyses of probabilistic models from the paper. The bounds themselves are of various complexities, but one nice takeaway is that the time taken to analyze these programs automatically is usually well under 1 second. This is good because real-world analyses need to run in a practical time frame. Now let's talk about some more empirical probabilistic modeling. Look back quickly at Mem and Bernoulli. If you squint a little, you might notice that Mem behaves a lot like Bernoulli, possibly terminating at each iteration. In fact, if we say that equality holds with 50% chance, then the runtime profiles of these 2 programs are pretty much the same. And note, the constant expected cost of 2 from Bernoulli is far better than the linear worst-case cost of Mem. This opens up another avenue for analysis using probability, approximating deterministic branches with probabilistic ones. If we can empirically determine that some code branches with a given probability, we can approximate it with a flip and use the Praml type system to get a better sense of the actual resource usage. In our implementation artifact, we include a mode for doing this, and we include some results of its application in our paper. For instance, insertion sort achieves linear time complexity on nearly sorted data. That's all I have. I now leave it to D for the close.
Thank you, David. In summary, in this paper, we have developed a probabilistic extension to the ARA type system. We overhauled the operational semantics to provide sound. We also implemented the result and applied it back to deterministic programs with empirical statistical techniques. In the paper, we also give one more application about automatic analysis of sample complexity. That is all we have the time to talk about, and thank you for listening to our talk. Stay healthy, and hopefully we can talk in person the next year.
Thank you, Dee and David. If you are watching this talk live, please don't forget about a Q&A session that may be available in your time band. Now, our next talk is entitled Program Sketching with Live Bidirectional Evaluation. Justin Lubin will present the talk, and he will introduce Smith, an example-based program synthesizer with support for sketching and no trace completeness requirement.
Hi everyone, my name is Justin Lubin, and I'm going to be presenting program sketching with live bidirectional evaluation. So this is a program synthesis project, and by program synthesis, I mean computer generation of programs satisfying a specification. So the two key words to take away here are satisfying and specification. So let's take a look at what I mean by those. By specification, I mean the user interface to a synthesizer. It's how the user provides a notion of correctness for a potential program. Satisfaction is then simply a program meeting these specification criteria. So let's take a look at two popular user interfaces to synthesizers, the first of which is logic-based synthesis. In logic-based synthesis, we provide a logical formula as a means of specification. So for example, if we're trying to specify the sort function, we might say that for all indices I in an array A of I has to be less than or equal to A of I plus 1. Satisfaction in logic-based synthesis is typically going to be static verification. So for example, we might use tools such as SMT solvers, dependent type checking, model checking, etc. Now, there have been many great logic-based synthesizers that have come out over the years. For example, Synquid, Rosette, Sketch, and Leon. These types of tools excel when we need to encode complex invariants about more complicated data structures, such as red-black trees. Let's take a look at another interface to program synthesis, example-based synthesis. In example-based synthesis, specification takes the form of input-output examples. Here, I've asserted that sort of the empty list is the empty list, and that sort of 312 is 123. Satisfaction will now take on the form of dynamic verification. So what we'll need to do is we'll need to test each input-output pair. We'll need to evaluate and check. And the keywords on this slide are evaluate and check. We'll definitely be returning to that later. So some really great example-based synthesizers that have come out include Myth, Escher, and Lambda Squared. For this project, we're going to be working in the domain of example-based, richly typed, general-purpose, functional program synthesis. Let's take a look at the current state of the art in this domain to see what we're up against, and that would be the Myth project. The way that Myth works is you give it a type signature and a set of input-output examples, and as output, you get a function that, when run, will satisfy those assertions. For the purposes of this talk, I'm more or less going to be treating Myth as a black box, one that will take in examples and give us a solution as output. Myth is a powerful program synthesizer, but it has two key limitations that we might like to address. Let's take a look at the first of these two. Given input-output examples, Myth will transform an empty program into a full solution. But what if we, as programmers, wanted to encode some domain-specific knowledge that we might have into a partial solution towards the program that we'd like to make? Then we'd like for Myth to transform this partial solution into a full solution. The idea here is known as program sketching. And it already exists for logic-based synthesis in untyped languages via the Sketch and Rosette projects, but we want sketching for example-based synthesis in a richly typed language. So to recap, program sketching is when you have a program with some holes in it, which might possibly be interdependent, and arbitrary assertions on this program, which is where we're going to derive our input-output examples, and what you get at the end of the day is a completed program. So let's take a look at Myth's second limitation, which is known as the trace completeness requirement. To be fair, this isn't just Myth that suffers from this problem. A lot of the program synthesizers that I mentioned earlier also have some sort of trace completeness requirement. So what is trace completeness? Well, a set of examples for a function is trace complete if, when the function is called on each example in the set, all its recursive calls also have an example in the set. Let's take a look at a small example. Let's say I have the length function as defined here, and I want to specify the example that length of 1561 is 4. Well, the problem is that length actually makes a recursive call here on the tail of its input. So I'm going to actually need to specify an example for length of 561. And similarly, I'm then going to need to specify an example for length of 61, and length of 1, and length of the empty list. So to recap, here are two limitations of Myth. First one is that it has no support for sketching, and the second is that it has this trace completeness requirement. But instead of framing these as limitations, what if we treated them as goals, and instead of saying that there was no support for sketching, we wanted to add support for sketching and remove the trace completeness requirement? Then we could call our system Smith. So what we'd like to do is provide Smith a sketch, which would be our first goal, and some non-trace complete examples, which would be our second goal, and get the same output as before. Let's take a look at how we can support this first goal, adding support for sketching. So here's how Smith is going to work. As a specification, we're going to give it a sketch and some assertions. And because Smith is example-based, we're going to need to do dynamic verification. As before, this means that we're going to need to test each assertion. We're going to evaluate and check. But here's where it gets tricky. What exactly do evaluating and checking mean when given a program sketch? Well, the answer to the first of these questions is live evaluation, which is theory that we draw from the Hazel project, which you can find at hazel.org. Let's take a look at how it works. Say we're given the program E on the left, which computes 10 plus 20 plus the first of this pair x, where x is 4, comma, a whole. Well, we can compute the 10 plus 20 and get 30 just fine, and then we can also take the first of this pair, which we know is going to be the concrete value 4. So we can get normal output, 34. Notationally, we would say that in the empty environment, E evaluates to 34. But what if we change the first of x to second of x? We can compute the 10 plus 20 just fine as before, but now second of x is going to give us a whole. In traditional programming systems, this would either result in an exception or a crash or some sort of meaningless output. But the key inside of live evaluation is that we can actually just evaluate around this whole. So because we have a whole in our input, we'll get a whole in our output, and we get 30 plus whole 0. Note that we also keep track of the environment around the whole at the time of evaluation, because that's going to be really useful for synthesis later. Notationally, we would say that in the empty environment, E live evaluates to 30 plus whole 0 with that environment. So that's how we can run these program sketches. But now how do we check these program sketches against the arbitrary assertions that we might have on them? Our answer to that is a novel mechanism that we call live unevaluation. Let's take a look at how live unevaluation works. Let's say we're given the same program before, E, and it evaluates to 30 plus that whole closure, whole 0. Well, if we want the entire program to be equal to 100, then we can actually transform this global constraint from an assertion onto a local constraint on the whole, namely that whole 0 needs to be 70. As a slightly more complicated example, let's say we have a program E that evaluates the first of some whole 1, and we want the entire program to evaluate to 8. We can transform this global constraint onto a local constraint on the whole, namely that whole 1 needs to be the pair 8, comma, top, where top is anything at all. Finally, let's take a look at our max program from before. If we want to assert that max of 1, 2 needs to be 2 with this program sketch, we can actually live evaluate it. So in the empty environment, we say that max 1, 2 live evaluates to whole 2 with the environment n equals 1, n equals 2, n prime equals 0. We live unevaluate the 2 onto this expression, and we get the whole constraint that whole 2 needs to be 2 in that environment that I mentioned earlier. So that's how live unevaluation works. Thus, satisfaction in Smith will look like live evaluation followed by live unevaluation. And it's the combination of these two concepts that we call live bidirectional evaluation. But as a satisfaction mechanism, live bidirectional evaluation actually introduces these new constraints x over here on the right-hand side. So let's take a look at a high level how this will fit into the program synthesis loop. In Smith, we're going to start with myth as a black box. Then, when the user provides a sketch, we can live evaluate it and get a result. We'll also collect these program examples from the assertion and live unevaluate them onto the result that we get. This process, which we call live bidirectional evaluation, will result on constraints on individual wholes that we can plug directly into myth. Then, if we augment myth with some additional rules to handle the partial solutions that we're looking for, we can actually get a partial solution from myth and some new program examples. Then, we can iterate this process until we arrive at a full solution. So, if we look back at our goals, we can see that live bidirectional evaluation enables us to add support for sketching. What about this trace completeness requirement? Well, it turns out that live bidirectional evaluation also solves this problem. To see how, let's take a closer look at trace completeness. Let's say we want to specify the function length using these two non-trace complete examples, as well as a blank sketch. The first step would be to live unevaluate these assertions and get the two whole constraints that when x is the empty list, whole 0 needs to be 0, and when x is 1, 5, 6, 1, whole 0 needs to be 4. Because Smith is not going to find a non-branching expression to satisfy this whole, it's going to introduce a case expression that splits on x's. Now, we'll live unevaluate these assertions again and get two new whole constraints, namely that when x is the empty list, whole 1 needs to be 0, and when tail is 5, 6, 1, among other things in the environment, whole 2 needs to be 4. Now this first hole constraint is very easy for Smith to solve. It can simply bind hole 1 to be the constant 0. That'll take care of this first constraint, so we no longer need to worry about it. The second constraint could be handled similarly, but Smith avoids overspecializing on large constants like 4 because they don't generalize well. So instead, it might try to synthesize the expression 1 plus length tail. But we run into a dilemma here. How can we be calling length on tail when we don't even know what length is, because that's the function that we're trying to synthesize in the first place? Here's where traditional program synthesizers could leverage the trace completeness requirement. If we were guaranteed to have the example that when x's is equal to 561, length of x's is going to be 3, then we could simply slot in 3 for length of tail and see that 1 plus 3 is going to satisfy our requirement that hole 2 needs to be equal to 4. But we don't have that example. So instead, the key insight is to realize that we actually do have a definition for length of x's. Length of x's is going to be equal to hole 0. In our partial solution, we see that hole 0 is going to be equal to this cache expression right here, which depends on hole 1 and hole 2. But nonetheless, we can run live bidirectional evaluation from before as usual on these programs because they're just normal sketches. Doing so will result in a new set of live unevaluation problems that we can just perform to get a set of new constraints. And it turns out that this program that we synthesized actually satisfies all of these generated constraints, as well as our original constraint that hole 2 needs to be 4. Therefore, all of our constraints have been taken care of, so we have a full solution for length. So that's how live bidirectional evaluation can also take care of the trace completeness requirement from Myth. So to wrap up, let's talk about some of the experiments that we ran to evaluate Smith. Here I'll be talking about 4 experiments that we ran based on the Myth benchmark suite. In the first experiment, we took the trace complete examples from the Myth benchmark suite that specified various functions and provided no additional sketching information to Smith. With this information, we could successfully synthesize 38 out of the 43 benchmarks from the Myth benchmark suite. In the paper, we talk about some hypotheses why we couldn't get that number up to 43. In our second experiment, we took these trace complete examples, but we removed as many as we could while still having Smith synthesize a correct solution. We found that with these non-trace complete examples, we could achieve a 61% specification size in Smith as compared to Myth. In our third experiment, we took just the recursive functions from the 38 that we could synthesize and provided a sketch of the base case to Smith. Then, like in experiment 2, we took the trace complete examples from experiment 1 and pared them down to a minimal subset that Smith needed to be able to synthesize the function correctly. Including the sketch of the base case, we found that we needed approximately a 46% specification size as compared to Myth. In our fourth experiment, we ran experiments 2 and 3 in the popular logic-based synthesizers Leon and Synquid. It's commonly said that logic-based synthesizers are strictly superior to example-based synthesizers because you can simply encode examples in logic as a conjunction of implications. While there is some truth to that sentiment, it's also true that many logic-based synthesizers are not well equipped to handle that kind of specification. And in fact, this experiment showed that while there were many tasks on which Leon and Synquid performed quite well, there were also many tasks on which they did not, particularly relating to non-trace complete examples. We hypothesized that combining the insights of live bidirectional evaluation with logic-based program synthesis could result in a system that has the power to specify complex data structure invariants while also having the ease of use of not having to specify trace complete examples. The last thing that I'd like to say is that these 4 experiments are a measure of expressivity, but we also ran experiments that tested the robustness of Smith, and these are described more in the paper. So that's Smith, an example-based program synthesizer with support for sketching and no trace completeness requirement. Here's an overview of what the system looks like, and here's a link to where you can find it on GitHub. You can also find me at jplubin on Twitter. I'd like to give a huge thanks to my collaborators Nick Collins, Cyrus Omar, and Ravi Chugh for helping me with this project, as well as the ICFP organizers and volunteers for making this conference possible. Lastly, I'd like to give a shout out to an event that I'm helping organize at ICFP, #ShutdownPL at ICFP. It'll be an anti-racism event occurring on Thursday, August 27th from 2 p.m. to 6 p.m. Eastern Time. I hope to see you there, and thanks for watching.
Thank you, Justin. And thanks a lot for organizing the anti-racism event, #ShutdownPL at ICFP. If you're watching this talk live, please don't forget about a Q&A session that may be available in your time band. Our next talk is entitled Elaboration with First-Class Implicit Function Types. Andreas Kovac will be presenting the talk.
Hello everyone, this is András Kovács and I will talk about elaboration with first-class implicit function types. In this talk, I will only give a rough overview of the paper and you can look at the paper for details. Let's explain the title of the talk a bit. First, what is elaboration? It is a translation from surface syntax to core syntax. Surface syntax is a parsed representation of what programmers actually see in a source file. It is usually compact and convenient to read and write, but omits a lot of typing information, and it is not necessarily well typed. The core syntax is used internally by the compiler. It is simple, well typed, and explicitly annotated, but it is much more verbose than the surface syntax. Elaboration can include inference, desugaring, instance resolution, and other things, but this talk mostly focuses on inference. In a setting with dependent types, people often use the term elaboration instead of type inference, because inference necessarily involves term inference as well, so type inference is a bit too specific. Second, what are implicit functions? These are functions such that arguments are given by inference by default and not by the programmer. In GHC Haskell, for all types are an example. These are functions abstracting over types or other type-level data. The arguments for all abstraction are inferred by default, as here, but we can also use visible type application to fall back to explicit arguments, as here. In GHC, type-level abstraction is always implicit and value-level functions are always explicit, but this restriction is specific to GHC and it is not something fundamental. In Agda, we likewise have implicit function types, but here we are free to make any function implicit or explicit, and type abstraction is just a special case of general dependent functions. Both in GHC and Agda, implicit function types control elaboration by signaling where inferred applications should be inserted. After elaboration, implicit functions are not that important anymore, because everything is fully explicit in the core syntax. Implicit function types are first class if they can be used the same way as any other type. In GHC, with rank and types enabled, we can use an implicit function as a function argument type, and in this case type inference also works fairly well. But what if we want to use an implicit function in some other parameterized data type, such as maybe, as in this particular example? This is not really possible in current GHC. There is a language extension called impredicative types, which technically allows writing down this type, but it is deprecated and doesn't actually work in practice. There is another talk at the current ICFP which introduces a new and practically usable implementation of this language extension. As a side note, users of lens libraries may be familiar with the examples on this slide. Lenses are polymorphic functions, so they can be used in higher order functions, but if we want to store them in data structures, then we have to use some new type wrappers. What happens in Agda? Here we can use implicit function types anywhere, so this type signature is completely fine. However, elaboration is not as smart as it could be, and the next line does not elaborate. Here we have to write out an implicit lambda abstraction in order to make Agda happy. The main contribution of this talk is a general solution which figures out such insertions of implicit lambdas. At this point, some people may note that the previous Agda example is an instance of something called impredicative inference, or impredicative polymorphism, which is a topic in the wider field of type inference. Indeed, the main point of this work is to provide a solution for impredicative inference. However, impredicativity means mostly orthogonal things in type theory and in the type inference literature. You can look at the paper for how exactly the two notions differ. I personally prefer to use the term impredicative in the technical type theoretic sense and talk instead about implicit functions in the context of type inference. With that said, to summarize the contributions of the current work, we have an elaboration algorithm, which supports strong inference for first-class implicit function types, or impredicative inference, and it also supports dependent types and global inference, which means that the whole module or program can be considered in inference and not just particular function applications, as in some previous works. The algorithm is also efficient, it uses no backtracking or iteration, and it actually traverses the pre-syntax exactly once. And lastly, the algorithm is a modest extension of bidirectional elaboration as implemented in Agda. Since the paper's algorithm is an extension of bidirectional elaboration, first we shall briefly talk about it, then look at its shortcomings with respect to handling first-class implicit functions, then finally look at the solution presented in the paper. Bidirectional elaboration consists of two functions defined by mutual recursion on surface syntax. Let's assume a surface expression t and a core context gamma. The purpose of elaboration is to create something in the core syntax from a surface expression. First, we have the infer function, which takes as input a core context and a surface expression and returns a core expression together with its core type. The check function additionally takes as input an expected core type and returns a core term with that type. When the expected type of an expression is already known, we use the check function, otherwise we use infer. This is similar to bidirectional type checking, but here each function also returns a core term. Let's look at a short example for how checking works. We use an informal monadic notation as we have as side effect the possibility of failure, and we also carry around as state a context of meta variables. Here we are checking a lambda expression with a function type. So what we do is to extend the context with a variable and check the function body with the codomain type. After this, we return a well-formed lambda expression. In general, the check function tries to push types inside constructors, which is beneficial for performance of elaboration and also for the locality of error messages. In the paper, the only change the elaborator can make on the input surface syntax is that it can insert implicit lambdas and implicit applications. As we will shortly see, this implicit insertion relies crucially on the bidirectional style. We won't look at the exact rules of elaboration here and instead look at some examples. First, let's look at an example for application insertion. Assume that we have the usual polymorphic identity function and we want to infer type for id applied to the boolean true. This expression is a function application, so first we infer a type for the function involved, which is id. Then we notice that the infer type is an implicit function type, so we insert an implicit application here. First, we create a fresh meta variable named alpha, then we apply the newly elaborated id expression to it. In the following, we will name meta variables using Greek letters. Now we have a function from alpha to alpha. This is good because we started elaborating an explicit function application, and now we have an inferred explicit function type for the left subterm of the application. What remains is to check the right subterm with the function domain type. Here we don't have any specific checking rule, so we change from checking to inference and infer type bool for true. Then we unify the expected alpha type with the inferred bool type. Now we can return the whole application as elaboration output together with the bool type. In general, whenever we have a bound or defined variable name with an implicit function type, when we use the name, implicit applications are inserted for the implicit arguments. Now let's look at an example for inserting an implicit lambda. We want to check this lambda expression with the usual polymorphic identity function type. First, we notice that the expression is not an implicit lambda, but rather an explicit lambda. So the expression as it is definitely does not have the expected checking type. However, we can wrap the expression in a newly inserted implicit lambda, so that's what we are going to do. We assume the implicit argument in the typing context and check the expression with the codomain of the checking type, which happens to be an explicit function type here. Now the types match up, so the checking succeeds and we return the expression with the inserted lambda. To summarize implicit insertion, when we infer an implicit function type, we may insert an implicit application, and when we check with an implicit function type, we may insert an implicit lambda. This has a nice symmetry and it performs in a fairly convenient and intuitive way in practice. Note that we don't always perform insertion in these two cases. For example, when we check an implicit lambda with an implicit function type, there is no need to do insertion. Again, for the exact rules, you can look at the paper. What can go wrong with this solution? Let's go back to the failing AGDA example. We also assume that we do not have a rule for checking a constructor of the maybe type. This is not necessarily always the case, and actually the most recent version of AGDA can handle this example fine, but we stick to this example for the sake of simplicity. Because we don't have a checking rule for just, we first infer type for this expression, then unify the infer type with the given annotation. The just constructor is polymorphic, so it has an implicit type argument, and we insert an application to a fresh meta variable. Next, we have to check the lambda x expression with the unknown alpha type. This is the key point of failure. The problem is that we cannot do lambda insertion at this point because the checking type is unknown. The only thing we can do is to infer an explicit function type for the lambda xx expression, but this fails to unify with the given type annotation. Likewise, we have a dual version of this problem. When the infer type is unknown, we cannot do application insertion. The solution is to represent unknown insertions in the core theory. With metavariables, we already have the ability to represent unknown terms, so we extend this to also cover unknown insertions. We add a strictly curried function type. This is a function type such that the domain is always a record type, and currying holds by definition. Here we have an example for how currying computes for this function type. The type on the left side has an empty record type as domain. We denote the record type as rec followed by a list of types. Here the list is empty, so we get the empty record type. This function type computes to just codomain type, so the trivial function argument disappears. For another example, if the domain is a record type with two fields, the function type computes to a function type with two implicit arguments. In general, a curried function type computes to an iterated implicit function type. There are also appropriate computation rules for term constructors, which follow the rules for types. Now we can represent an unknown number of implicit arguments by putting a metavariable in the domain. We use this to improve on elaboration. Previously, unknown types always prevented implicit insertion. We change this as follows. When we check with an unknown type, we insert an unknown number of lambdas using the strictly curried function type. Concretely, we insert a strictly curried lambda, which may compute later to 0 or more implicit lambdas. Changing lambda insertion this way is easy to implement and improves inference in a large number of practically interesting cases. However, we don't enhance application insertion and leave that to future work. The reason is that unknown application insertion yields rather complex unification problems, which could be a line of research on its own. Now, the running example is elaborated without issues. In the infer type for the expression, the rec alpha stands for an unknown number of implicit arguments. Also, the unknown beta type can now depend on the argument. Then, we unify the inferred and expected types. For strictly curried functions, unification tries to match the two sides of the equation by solving curried function domains. In this case, the domain is solved to unary record, which contains a set. So unification succeeds and we get the expected elaboration output. We are nearing the end of the talk, so let's revisit this picture about elaboration to provide a summary. This picture is actually not quite correct. In practical implementations, the core syntax which is used for optimizations and further compilation is not the same as the core syntax used in elaboration. We instead have a picture like this. We use a slightly larger and more complicated core theory for the purpose of elaboration. Implicit function types provide control over implicit insertions, and metavariables allow representing unknown terms. However, this core theory is also a nice and well-behaved type theory. This is in fact a modal type theory, since metavariables and metacontexts form a so-called crisp modality, or alternatively a contextual modality. If we don't use metavariables and we only use bidirectional type checking, then inference becomes rather limited. Metavariables are the natural solution for representing unknown terms, and they are a basic ingredient in implementing more sophisticated inference. It is also important to note that if we successfully finish elaboration, all metavariables are solved, and we can also just ignore or translate away implicit function types. So the extra features don't affect downstream compilation. If we allow first-class implicit function types, that causes implicit insertion to be more dynamic and more interleaved in the elaboration algorithm. Therefore, if we want to have robust inference with first-class implicit function types, we need to represent unknown implicit insertions. Strictly curried function types provide a natural and tight representation. Additionally, strictly curried functions are a modest extension of type theory, so we still have a well-behaved and computationally adequate core theory. And like the other extra features, strictly curried functions also disappear after elaboration. My impression is that if we want to have robust impredicative inference, strictly curried functions are a basic ingredient, similarly to how metavariables are a basic ingredient for general inference. Without this basic building block, potential solutions are significantly limited in power and efficiency.
Thank you, Andreas. If you are watching this talk live, Be sure to join the Q&A session with the author if it is available in your time zone. The last talk of this session is entitled Kinds are Calling Conventions. Paul Downen will present the talk.
Hi, I'm Paul Downen, and I'll be telling you about how kinds can express calling conventions in programming languages. Functional languages make calling functions simple and easy, but there are many different parameter passing techniques which impact the performance of function calls. And because these are pervasive in functional languages, it's important to make them efficient. To implement a function call, we need to be able to answer some basic questions about its arguments. First, what is the argument's representation at runtime? It could be an address, character, floating point number, etc. And how big is it? For example, it could be just 1 byte or a 64-bit word. We also need to know where is it stored. It might be in a specialized floating point register, or it could be a pointer into the heap. For the function being called, we need to know its arity, which is how many arguments are needed before its code can be properly executed. We also need to know how many arguments can be passed simultaneously. Should they be passed all at once in multiple chunks or individually, one at a time? Lastly, we need to know the levity, by which I mean to say the evaluation strategy of the argument. For example, eager languages use call by value, and lazy languages use call by need evaluation. Laziness in particular has an overhead that might not be necessary for a strict function. Moreover, we will see that evaluation strategy interacts with arity as well as representation. Since it's probably the least understood of these three topics, I will focus primarily on arity in this talk. Arity is not always so simple to see. Consider these 4 functions of the same type. Their type suggests they have arity too. They need 2 arguments before they produce a result. But this type might leave out important operational details that we only learn from the function definitions. Look at the definition of f1. It starts with 2 lambdas, so it requires 2 arguments before doing any interesting work. So f1 definitely has arity too. Now look at f2. It only starts with 1 lambda. However, all it does is call f1. So it also requires 2 arguments before doing any work. In fact, we can eta expand f2, and doing so does not change its meaning or runtime behavior. This sound eta expansion makes it clear that f2 also has arity too. f3 is very similar to f1, but with an important difference. f3 starts with only 1 lambda for binding x. Then it does some work on x before requesting the next argument y. So, what is f3's arity? As a hint, consider that expensive of x might be costly to compute, as the name suggests, and it might even cause side effects in a language like OCaml. For this reason, f3 only has arity 1. f4 is defined similarly to f2. However, this time, the eta expansion is not sound. That's because f3 can do some serious work with only 1 argument, so f4 also has arity 1. Based on those examples, let's try to come up with some informal, intuitive definitions about what arity is meant to capture. First, we already use the intuition of serious work when analyzing the arity of a function. For example, if f applied to 1, 2, and 3 does work, but f applied to only 1 and 2 does not, then f has arity 3. Second, we sometimes need to use eta expansion to see the full arity of eta-reduced function definitions. So, if f is equivalent to its thrice eta expanded form, as shown here, then f has arity 3. Note that we need to be careful. Sometimes this eta expansion might not be sound, because it could change the behavior or the cost of a function. This is especially true in languages with effects, but even pure languages like Haskell care about efficiency, so we have to be careful there too. Third, in an operational sense, arity tells us the number of arguments that can be passed to a function simultaneously in a single call. For example, if f has arity 3, then f applied to 1, 2, and 3 can be compiled into a single function call, rather than a chain of 3 partial applications. Now, focus on definitions 2 and 3. They serve as the main backbone for our idea. Definition 3 suggests that arity is important for performance. There's a reduced cost for calling functions of higher arity. Whereas definition 2 says that arity can be seen in terms of the eta law of the lambda calculus. The arity of a function corresponds to the number of valid eta expansions. Taken together, making more eta expansions valid can improve the arity and thus performance of function calls in a language. This link sets up our goal in the context of an intermediate language for an optimizing compiler. However arity analysis is done, that information must somehow be expressed inside of the internal code used in the compiler. We can do this with an ultimatum. Eta expansion is always valid. That way there are no more corner cases to worry about, and so arity is always the largest number that makes sense for any function. However, we can't lose what we already had. Practical compilers place restrictions on beta reduction that are crucial for algorithmic complexity. Therefore, our goal is to have an intermediate language with unrestricted eta expansion for functions, but alongside restricted beta reduction for arguments of other types. Here is our general approach to the design of an arity-aware intermediate language. First, we add a new type for primitive functions denoted by the squiggly arrow rather than the normal straight arrow to help distinguish them from functions in the source programming language that have a slightly different semantics. In particular, primitive functions are fully extensional, and this is different from the functions in normal programming languages like Haskell and OCaml, where the eta law might not apply to all expressions of a function type. However, application may still be restricted for efficiency for the purposes of language's semantics. So, for example, in the case where a parameter is used more than once. If you apply the function lambda x applied to x, to an expensive argument, it doesn't need to be recomputed for both uses of x. Because of unrestricted eta, types can now express the arity of functions. All you have to do is count the arrows. For example, if f has the type int to bool to string, we know that it has arity 2 already without even looking at f's definition. But just having unrestricted eta isn't enough for practical compilation. That's because there are some instances where we intentionally want to lower the arity for a different behavior or better algorithmic complexity. For example, recall f3 from before. Its definition was conspicuously written as an arity 1 function, just so that the expensive computation of z can be shared and reused for many different values of y. But applying eta expansion, which is now always allowed, means that f3 has arity 2, not 1. If we use a partial application of f3 many times, like mapping it over a large list here, it will recompute expensive of 100 over and over. That's bad. We solve this problem by adding another type for representing explicit closures. Here we denote the closure of a type with curly braces. They are introduced with the clause constructor, and that lets us wrap up a unary function from int to int inside of a closure of the same type. Including closures in the result of a function let us intentionally break up its arity when partial applications matter, like in f3 prime. This is an arity 1 function taking the first argument and returning a closure of another arity 1 function that takes the second argument. This closure is then later used with an explicit app operation. So you can take the closure returned by f3 prime of 100 and then apply it to the second argument to get a result. Now, the partial application of f3 prime computes expensive of 100 only once, even though the reclosure it returns is reused many times. But there's a subtle impact of allowing all of these extra eta expansions. For example, consider this definition that binds a function f to the apparent computation expensive of 100. F is used several times within its scope, so when exactly is expensive of 100 evaluated? That depends on the evaluation strategy of this let binding. Under call by value, the right-hand side expensive of 100 must be computed first, before a value can be bound to f. Instead, under call by need evaluation, the right-hand side is evaluated later only when f is first needed, but its value is remembered so that it never gets re-evaluated on future uses of f. Slightly different is call by name evaluation. There, the right-hand side is still evaluated later when f is used, but it's also re-evaluated every single time that f is used. But remember, in this language, eta expansion is always valid, so the definition of x above is actually the same as x prime here. But look at x prime. The evaluation of f definitely follows a call by name order because the eta expanded right-hand side is manifestly a value. That means that expensive of 100 will be recomputed every single time f is called. Therefore, the operational consequence of allowing unrestricted eta for primitive functions means that they cannot be evaluated for any old reason, like in a strict let binding here or the seek operation in Haskell. Primitive functions can only be evaluated when they are called with all of their arguments. When we link up the high-level notion of arity about eta expansion With a low-level notion about simultaneous parameter passing, we need to be careful about polymorphism. Consider this polymorphic definition. It takes a function f that returns an arbitrary type A and applies it twice. This is done through the local definition of g, which is the partial application of f to 3. Now, what are the arities of f and g? Well, I said we could just count the arrows in the types, so f's type has 2 arrows in it, so it has arity 2, and g's type is int to a, so it has arity 1. This seems sensible at first, but what happens when the polymorphic a gets instantiated with a concrete type? For example, a might be instantiated with another function type like bool to bool. Well, when we do this, now f's type suddenly has 3 arrows in it, so its arity has changed to 3, and g's type becomes int to bool, so now the arity is 2 instead of the original 1. This is a big problem. We want to be able to statically compile function calls as passing multiple arguments and jumping to the code of the function. If we look at the application of g to 5 and g to 4, how do we compile those calls? If g's arity is 1, then this is a complete function call. But if its arity somehow becomes 2, then there suddenly aren't enough arguments to correctly execute the body of g. How can we possibly statically compile multi-argument function calls when the arity of functions isn't even stable? These shortcomings can be overcome with more polymorphism. The idea is to encode the intentional details of types, like the runtime representations and calling conventions, into their kind. First, we can generalize the basic kind of types, usually written as star, to the more detailed form type RC. R stands for the runtime representation of the type A. It could be a primitive representation like a pointer or an integer, or it could be something compound like an unboxed tuple. C stands for the calling convention of A, which spells out how those values can be invoked. So for example, if we have an unknown type variable A, we can give it a kind like type pointer call of n. This says that the values of type A are represented as pointers at runtime, and that those values can be called with n arguments. Note that representing the arity as a single number is slightly simplified from the full system in the paper, which presents all the details. Now that the arity appears explicitly in the types, it can be used to resolve the ambiguity that came from polymorphism. For example, let's return to the troublesome poly definition from before. We can now pin down a specific arity for the generic type variable A introduced by the for all. Here we say that the generic type A is called with 2 arguments. Even though the type of A is abstract, its kind makes it clear that f has arity 4. That's counting for the 2 known integers in the type of f, plus 2 more from the return type A. Also, g has the type int to a, but we know it has arity 3. So it takes 1 known integer argument plus 2 more arguments from the return type A. Furthermore, since the calling convention appears in the types, we can also abstract over them. For example, the revapp function here supplies an argument x to a function f. Does this type make sense? The function f has the type a to b, and to generate the code for calling f, we need to know its arity. Since f takes an argument a, and b already has arity 1, this adds up to an arity of 2. The argument x has the type a. To pass it around, we need to know its representation. The kind of a is type pointer c, so we know that x is represented as a pointer. But we don't know the calling convention of x. That's fine, because revapp doesn't call x itself. It just passes x around. If you found this talk interesting, here is even more material in the paper. I was only able to talk about calling conventions and a little bit about representations, but we express levity in this kind system too. This lets us accommodate both eager and lazy functional languages with the exact same shared intermediate language. We also describe a compiler pipeline, along with its correctness, from a simple source language to the intermediate language, and finally to a low-level target language. This compilation depends on types and kinds, so we use a type system to ensure that static compilation is always possible for every single well-typed program. In the end, we can say that kinds give us a formal and high-level language for capturing the details of efficient calling conventions for functions. Thank you for your attention.
Thank you, Paul. If you are watching this talk live, please don't forget about a Q&A session that may be available in your time band. This is the last paper in session 6. Thank you for attending.
Well, we've made it to the end of the ICFP technical program, but this isn't the end of the week. Please stick around for the symposium and workshops that are happening tomorrow and the next day. There's still a lot more ICFP to be had. But at this point, I'd like to take a moment to thank the many people who have helped me over the past few months put this conference together. I first want to thank our sponsors, Jane Street, IRIF, Standard Chartered, Facebook, Galois, Bloomberg, Microsoft, Oracle, Twig, Erlang, and IntelliFactory. In fact, you can thank our sponsors too in person in the industrial reception, which is up next in the program. I particularly want to thank our program chair, Adam Shapala, who, in addition to all of the tremendous amount of work that goes into putting together the program for a conference like ICFP, also stepped up to join my virtualization committee. This is a group of people who got together all through the summer to help figure out what it means to have a virtual conference in the first place. So I particularly want to thank Benjamin Pierce, Nikki Vazu, Alan Jeffrey, and Soo-Kyung Roo, who have been the prime group helping me to identify what do we need to do to make ICFP an online experience available for everyone. We've been fortunate to have the Clouder tool available to host virtual ICFP. This tool is an open source project started at the beginning of the coronavirus. It's been developed mainly by John Bell, Krista Lopes, and Benjamin Pierce. They are developing it primarily for academic conferences like ICFP, and they have put in a large amount of work tailoring this platform for ICFP's specific needs this week. So I'm very grateful for all of the work that they have done. Making the Clouder platform work in conjunction with all of the other tools, such as YouTube and Zoom and Bilibili and Ishi, has been thanks to our AV team. We have Harry Goldstein, who has stepped up to understand the interactions between all of those tools. We have Yishuai Li, Zhizheng Hu, Rufeng Xi, Vin Hao Tang, who have helped us stream to Chinese-friendly servers. We have Alan Jeffrey and Lindsay Cooper, who put together the captioning that we had on all parts of the ICFP program. Victor Landvin did the video editing, and Leif Anderson gave us support for accessing the ACM SIGPlan YouTube channel. In addition to the aspects related to virtualization, we also have the rest of the organizing committee doing fairly normal roles. So Yu Kong put together the student research competition. Alan Jeffrey, in addition to being on the virtualization committee and helping out with accessibility, is also our industrial relations chair. So he has put a lot of work into ICFP this summer. Jennifer Hackett and Leonidas Lampropoulos were our workshop co-chairs and also helped with organizing our tutorials and social events as well. We heard from Igor Lukadin, our programming contest organizer, and Sam Tobin-Hochstab is our publicity chair and all-around researcher expert helping us maintain the ICFP program. Annabelle Satin helped us at the beginning when we thought we were going to be able to hold this at a hotel in New Jersey. And Talia Ringer joined in a new role on the organizing committee, putting together a fantastic new mentoring program that I hope ICFP will be able to continue in every year to come. Last but not least, I want to also point out that Yu Kong was the main organizer for the ICFP music video. We are assisted during this week by our student volunteers who we would not be able to run this conference without. These student volunteers have been coordinated by our able and capable student volunteer captains. So I particularly want to thank Hannalie Tavant, Victor Lanvin, and Jaemin Hong, who have organized our student volunteers across 3 different continents and given them instructions so that they can help in every aspect of running this very complicated but still exciting week. And I want to put up the names of our many, many student volunteers. Please say hello to them. If you see them on Clowder and elsewhere, we would not be able to run ICFP without them. I also want to give thanks to the event organizers for our co-located events, the Haskell Symposium and the associated workshops that go along with ICFP. This is a fun week because there's always a lot going on, and it's thanks to these folks who put together the programs for Sunday and Thursday and Friday so that we have a full week of ICFP fun. We also new this year have many social events, which I think are very important to have in a virtual conference. And so I definitely want to give thanks to anyone who has put together, who has provided us with ways to interact with each other online. It's not the way we really would prefer, but it definitely adds to our experience as we are in this online platform. We also put out a very late call for tutorials, and we got 10 proposals for tutorials to help us dive into many different topics related to functional programming in depth. And our final person I want to thank is you, everybody who has come to virtual ICFP, who's logged into the Clowder platform, who participates in the online chats and the video discussions. You are what makes ICFP fun, and I'm glad to have you here. So again, this is the end of the ICFP main program, but it's not the end of the week. Please stick around, and I'll see you tomorrow for even more ICFP fun.